Hello everyone, welcome in the lecture of the shear wall design. Basically in this lecture we are going to learn that what is the definition of the shear wall, how we can design the shear wall in Etabs. Also we are going to look at that what are the different type of the shear wall we are having. Also we will see that what is the difference between a shear wall and the columns. In this lecture also we will look at that what is the best locations where we can put the shear wall in our building. Also we will discuss about the poor locations where it is not advisable to put the shear wall in our building. We will also discuss about that what are the different shapes of the shear wall we are having. Now let us first of all start with the shear wall design definitions. So we are going to first of all see that what is the definition of the shear wall. Now if you look at the definition of the shear wall, it is there that a shear wall is a structural element that provides a lateral resistance to the horizontal forces acting on the building or structure such as wind, load or seismic forces. It is a vertical wall or panel designed to withstand the shear forces induced by these lateral loads and transfer them to the foundations. In the simple meaning, if I will define the shear wall, a shear wall is a structural element. How your beam and column is a structural element, like that your shear wall is also a structural element which is used to resist the lateral forces coming to the building. So lateral forces may be your earthquake forces or maybe it will be wind forces. So when these forces coming to this building, it is going to resist that forces. So how your column is a vertical element, like that the shear wall is also a vertical element. But shear wall generally used to resist the lateral forces coming to the building. So it is also resist the vertical forces also, but mainly we design shear wall to resist the lateral forces. We provide shear wall to resist the lateral forces in our building. Now the next is your function of shear wall. So the first function is that providing lateral strength to the building. So when you provide the shear wall, what is going to happen? It will provide a lateral strength to the building. So it will resist the horizontal forces like earthquake, wind, and transfer these forces to the foundations. So this is the first function of the shear wall, to provide lateral strength to the building. Now let us look at the second function of the shear wall, which is providing lateral stiffness to the building. So when you provide the shear wall in the building, what is going to happen? It is going to increase the stiffness of that particular directions due to the shear wall. So if you look at the further line here, shear walls provide large stiffness to the building in the direction of their orientations. So in which orientations you have put that shear wall, in that particular directions the stiffness of that building is going to increase. So what is the resultant? The resultant is that which reduce the lateral sway of the building and thus reduce the damage to the structures. So when you provide the shear wall in the particular directions of their orientation, in that direction the lateral stiffness is going to increase, and which is going to reduce the lateral sway of the building and reduce the damage to the structures. So I'm going to show you that what actually means here. So now I'm going to open Etabs and show you. Let's suppose that I have one structure here, and if you look at here that we have put our shear wall in the Y also and in the X also. So if you look at, we have put our shear wall in the Y and X, both of the directions. So when you put the shear wall in either of the direction, in the particular direction the lateral stiffness of the building is going to increase. So let's suppose that if you put the shear wall in these directions, then in these particular directions, let's suppose that this is Y directions, so in these directions your lateral stiffness of the building is going to increase. Now let us come to the PPT which we are discussing. Now I think you have clearly understood that what is the definition of the shear wall and what all the functions of the shear wall are there. Now we will go to the technical part of the shear wall. So this was just a definitions and the function of the shear wall. Now we will look at the next is that what is the difference between a column and the shear wall. I have already discussed that both columns and shear wall are the structural element of the building, and these are the vertical structural element which is going to resist the forces coming to the building. So it may be a vertical forces or it may be a horizontal forces like earthquake forces or the wind forces. So both of the structural element will resist the forces in our building. So don't think that column is not going to resist the forces. Column is going to resist the forces. But what makes difference? So what is the difference between a column and the shear wall? If column is also going to resist the forces, then what makes shear wall different from the columns? That is the questions, right? So both of the structural element is going to resist the lateral forces coming to the building. Column also and the shear wall also. But very important thing I would like to notice here that if I have any wall and that wall is subjected to the lateral forces, then I will call that wall is a shear wall. But if I have another type of wall and that wall is not subjected to the lateral forces, or I'm not going to design that wall to be as a subjected to a lateral forces, so in that case I will not call that wall as a shear wall. So for confirming wall as a shear wall, you have to induce the lateral forces in that, or you have to design that wall as a lateral forces, then only that wall will be called as a shear wall. That is very important thing you have to notice here. Now when it comes to the difference between a columns and the shear wall, so what is the difference, on what aspect we are going to differ these two of the structural element? That is the first thing we have to discuss it here. So the first aspect is on the basis of the bending moment which we are getting in the columns and the shear wall. So we are getting different type of the bending moment in the columns and the shear wall. So this bending moment which just given a screenshot here is of column. So this bending moment which I am just showing you is of column, and this bending moment which I am just making here of shear wall. So on the basis of the bending moment, or we can say on the basis of moment distributions, we are going to distinguish between a column and shear wall. So two the structural element is going to differ on the basis of the bending moment which it is getting in their structural configurations. Now if you carefully watch the moment distribution in the column, or we can say a bending moment in the column, you will find very important thing that the point of counterflexure. The point of counterflexure means where the bending moment is going to be a 0, or we can say where the bending moment is going to change from negative to positive. That is the point where you will find a 0 bending moment. You will find in the column that point of counterflexure where the bending moment is going to be 0 in the middle of the story. So if you look at that here also, you will find every column the point of counterflexure is in the middle of the columns. So the first difference is that the point of counterflexure in the columns you will find in the middle of the story for the columns, so that the maximum bending moment will be in the top or in the bottom for the columns. So we can conclude here that in the column the formation of the plastic hinges or the yielding will be in the bottom or at the top of the story of your column. So the formation of plastic hinges or yielding will be at the top and the bottom of your columns when the lateral forces is induced in the columns. Now if we consider same thing in the shear wall, you will find something different here. So what difference is that the maximum bending moment in your column will be in the bottom of your story. So let's suppose that I have one shear wall here and I have shown the bending moment of this shear wall here. You will find that maximum bending moment you are getting somewhere in the bottom of your story. So this is the difference here. Now we can calculate here that the maximum bending moment you will find in the bottom story of the shear wall, and the formation of hinges or yielding will be occurred in the bottom story of the shear wall. This is the difference between a bending moment of the columns and the shear wall. You have understood it carefully. Now let us understand this difference in Etabs also. So I am going to explain the same difference by taking a bending moment of the columns, and also I will take it the bending moment for the shear wall also, and also I will make it the same difference how it will be appear in Etabs. So let us open Etabs here and let us look at the first of all bending moment for the columns. So you go to the show frame forces here, you select the load cases. Let us suppose we are selecting the earthquake load cases here. Select the bending moment M33, tick here frames, apply it. So you can look at here that the bending moment how actually it is for the columns. So you will find here that the bending moment of the columns, you will get it maximum in top and bottom, and the point of counterflexure will be in the middle of your columns. So this is going to be common for all the columns here. Now same thing if you are going to look at for the shear wall, you will find something different here. For looking the bending moment for the columns, again go for display frame forces here and select, instead of frame select piers and apply it. Now if you are going to look at the bending moment of this shear wall, you will find here that maximum bending moment you are getting in the bottom of the story. So if you compare the maximum bending moment, you will find that you will be getting in the bottom of the story here. So that the formation of plastic hinges, or we can say yielding, will be occurred in bottom of the story. So I think you're very clear about what is the difference between a columns and the shear wall in consideration of bending moment. Also, I would like to tell you that a shear wall mainly resisting lateral loads by bending only. So also we can call shear wall as a bending wall also, because generally it is going to resist the lateral forces by bending only. Now I think you are very clear about what is the difference between a columns bending moment and the shear wall bending moment, and this only make it difference between columns and the shear wall. Now let us look at the second difference. But before going into the second difference, one very important thing you have to clear that this difference will not get validated in the technical part. So this difference I will not count as a technical difference here, because this is just like a physical appearance difference. So what actually it is, if the length to the thickness ratio, let's suppose that I have a length of 3 meter and the thickness or depth is of having a 300 mm. So it will be 0.3. If you divide, or we can say if you take the ratio, and if ratio is coming equal to or greater than 6, then we can design that things as a shear wall. Okay, so if you just divide it, it is coming 10, then you will design that part as a shear wall. This is the difference. Now this is not a technical difference here, this is just like appearance difference. Like if you're getting some scenario where the length of your thing is coming 3 meter and depth is 300 mm, so in that case you can design that as a shear wall, but technically this is not validated. Technically difference is this only, that in the case of the bending moment, if you're getting the different bending moment in the columns and the shear wall, that is the main technical difference here. But this is not technical difference, I will say here. This is like a physical difference, or you can model it as a shear wall, like the difference it is. So don't consider this as a technical difference, consider this only as a technical difference. Now let us come to the next part, which is the poor placement of the shear wall. Now while placing the shear wall in the building, we have to follow some guidelines. Don't blindly put the shear wall in their building. If you're putting like that, then your building will get torsion. So avoid placing your shear wall in the poor directions. Now let us take some of the example where you have to avoid the poor placement of the shear wall in your building. So there are some logic behind while putting the shear wall in the building. Now what I have told you in the previous discussions also, so that whenever you are putting the shear wall in the building, in that direction of their orientation, the lateral stiffness is increased. So let's suppose that I have a plane here of x directions, and this is the plane I have in the y directions here. Now you can look at that in this both plane, you will find here that your y directions lateral stiffness has been increased more compared to the x directions here, and also in the corner the stiffness is higher here. If you just look at that, at the corner point your stiffness is higher. Now what we have studied that your stiffness, lateral stiffness, should be distributed uniformly in your structural configuration. You can find here that in the corner positions the stiffness of the building has been increased larger as compared to other positions here. So there is no any uniform distribution of the lateral stiffness in our building. Now I am going to model the same case in our Etabs model. So how the placement of the shear wall done in the first case, I have modeled it the same positions in our Etabs here. So if you're going to look at here, that you can just see that we have given a shear wall at the corner, and also we have put our shear wall at these positions. So now we will look at the adverse effect of putting the shear wall like that. Now if you're going to see the mode behavior of this building, you will find that the first mode only you will get a torsion mode. So as you already know that the first two modes should be a translations mode for the regular building, but if you're going to see the mode behavior of this building as a first mode, you will find there will be a torsion here. So if you go and show deform shape here, and if you just look at the mode 1 behavior and you will just animate this, you will find that the first mode only you are getting as a torsional mode. and also you can just see that your maximum stiffness is shifted at these positions here. So looking animations, you can clearly understand that this building mode behavior is not regular behavior. So due to this building will have a torsional effect. Now let us come back to the PPT and look at the second case here. In the second case also you can look at that the lateral stiffness is not distributed uniformly in our building. So if you just look at that, in this particular directions only the shear wall has been placed. So there will be one more shear wall should be there in the parallel directions also, and if it is not there, then this also will create a torsion to this building. So this case also is a poor placement of the shear wall. Third case also you can look at that they have not distributed the lateral stiffness uniformly. So there also should given a parallel shear wall so that your lateral stiffness should be distributed uniformly. So both of the three cases are just a case where there is a no uniform distribution of the lateral stiffness are done in the building. So whenever you are putting the shear wall, you have to look at that you have distributed the lateral stiffness uniformly in your building. If you just put the shear wall at one position and if you are thinking that your building will not get in torsion, then that is wrong. So whenever you are going to plan to put the shear wall in your building, you have to carefully watch that you have uniformly distributed the lateral stiffness in your building or not. So let's suppose that I have to plan to put the shear wall in our building. So I will look at that in all the particular directions, or we can say in all the particular planar axis, I have uniformly distributed the stiffness or not. It should not be like that in particular directions or particular axis we have put the more stiffness. So what will happen? It is going to adverse the effect here. So in the particular directions your stiffness will be more as compared to the another directions here or another axis. So that will create a torsion to the building. So that is the most important thing you have to look at, that you have uniformly distributed the lateral stiffness to the building or not. So this is the first thing you have to look at whenever you are going to put the shear wall in your building. So I will always recommend you that please uniformly distribute the lateral stiffness in your building. That is the first thing you have to do it. Now let us look at the ideal location of putting the shear wall in our building. So what could be the ideal locations? Now I have already discussed in the poor location that when you are putting the shear wall and if you are distributing the shear wall lateral stiffness ununiformly, at that time you will get a torsion in the building. So if you are going to avoid the ununiform distribution of the stiffness, you will get a good locations of putting the shear wall in your building. So the first case you can look at it that a shear wall should be placed symmetrically in the plan. So when you are going to put the shear wall symmetrically in the plan, at that time you will get a good layout of the shear wall in your building. So you will not get a torsional effect in your building. So when you are going to put the shear wall symmetrically in the plan, at that time there will be no torsion in your building, or we can say there will be less chance of getting torsional effect in your building. And the second case, when you are moving, or we can say that when you are putting the shear wall as far as from central stiffness, then also that will be a good location of the putting the shear wall. But I will recommend you to try the first thing only, that put the shear wall symmetrically in the plan. So when you are going to put the shear wall symmetrically in the plan, at that time your torsional effect will get reduced in the building. So that will be a good options of putting the shear wall in your building. So whenever you are going to put the shear wall, you have to uniformly distribute the lateral stiffness in all the plan. If you are not going to do that, you will get a torsional effect in your building, and that will create a damage, or we can say that is not good for proper building. So what could be a ideal layout of the shear wall? The ideal layout of the shear wall will be putting the shear wall symmetrically in the plan, and that will get a uniform distribution of lateral stiffness in your building. Now let us move to the next important topic, which is your shape of the shear wall. So we will look at that what are the different shape of the shear wall which is used in our building. The first important shape is your rectangular shape, and this is the most common used shape in our building. So this type of the shear wall you will find every building, or we can say maximum of the shear wall you will find in this shape only. Now the second shape, it is a barbell shape. So this is going to be similar how it is a rectangular shape, but at the end you will find a bulb like structure which is used to resist the stresses coming to this shear wall. Now this shear wall generally nowadays it is not used. So instead of giving this bulb type at the end, we give it a boundary element in the rectangular shapes only. So if the stresses are increasing, at that time we provide a boundary element in the rectangular shape only. So generally you will not find this barbell shape nowadays. Instead of that you will find rectangular shape. At the end there will be a boundary element to take the stresses coming to this shear wall. So this bulb type of structures which you are looking here, it was used to resist the stresses coming to the shear wall. Nowadays what they are going to use, they will use a rectangular shape shear wall only, and at the end they will provide a boundary element which will resist these stresses coming to this shear wall. Now I think it is very clear to you. Now let us move to the flank walls, which is T shape, L shape, C shape, I shape. So these are T shape shear wall, L shape shear wall, C shape shear wall and I shape shear wall. So this type of the shear wall also we use it in our building. Now the last we can say possible configuration of the shear wall is of core wall. So you can look at that, this is the type of core wall here, and there is a opening here in this core wall, and in this opening there is a connected beam here, and we call this as a coupling beam. So you can look at that, these two shear wall are connected with this coupling beam, and this we generally call as a core wall here. So in the case where there is a lift, we generally use this type of the shear wall.